Hi, everybody. Today we're going to talk about Section 3-3, Measures of Relative Standing and Box Plots. We have what's called a Z-score, and it's a score that we use to standardize all the values. When we do our bell curve, and we look at the middle, which remember is the mean, and we have one standard deviation, two standard deviations, three standard deviations on both sides. Also, what that is our Z-scores. A Z-scored is the number of standard deviations that a given value X is above or below the mean. The Z-score is calculated by using one of the following. All we're going to do is use our calculator and find our Z-score. We're going to subtract whatever our value is minus the mean. The same for both. It just, the symbols change depending on sample or population, and we're going to divide by the standard deviation. And we're always going to round it to 2 decimal places. Important properties of Z-scores. A Z-score is the number of standard deviations that a given value X is above or below the mean. Z-scores are expressed as numbers with no units. They're just a number. A data value is significantly low if its Z-score is less than or equal to -2, or high if the Z-score is greater than or equal to +2. Again, if we have our bell curve, and this is our 0, that's our 0, which is our mean. Let's say this is -2, and this is +2. Anything that is to the left of -2 or the right of +2 would be considered significantly high or significantly low. If an individual data value is less than the mean, its corresponding Z-value is a negative number. We're always going to use that X minus X bar because anything this way is a negative number and anything to this side is a positive number for our Z-scores. Let's do an example. Comparing a baby's weight and an adult body temperature. Which of the 2 data values is more extreme relative to the data set from which it came? Now notice, we don't really have to worry about the fact that they're not related, because what we're going to do is just find their Z-scores. Which of the following data sets is more extreme relative to the data set from which it came? First thing we want to do is we're going to find our Z-score. Our Z-score is going to be equal to X minus X bar over S, which is equal to, our X value is 4,000 grams. Our X bar is 3,152 grams. And we're going to divide that by 693.4 grams. I get 1.22. That's my Z-score for this newborn baby who weighs 4,000 grams. Let's do the same exact thing here for our adult temperature. We have Z equals X minus X bar over S. We have 99 minus 98.2 divided by 0.62. This is 1.29. If we compare 1.22 to 1.29, here's our bell curve. It's also called our normal curve. Here's 0, here's 1, and here's 2. Let's say this is 1.22, and this right here is 1.29. And the question that we were asked is, Which of the following two data values is more extreme relative to the data set which it came from? The one that's more extreme is the 1.29 because it's further away from the mean. The answer to this problem is going to be adult temperature. Someone with a 99-degree temperature than a baby who weighs 4,000 grams. It's not that they're extreme, it's just that this number is larger than this number, so this one is more extreme. Not significantly high or significantly low, but more extreme. This is their interpretation. The z-score shows that 4,000 gram birth weight is 1.22 standard deviations above the mean, and the 99-degree body temperature is 1.29 standard deviations above the mean. Because the body temperature is further above the mean, it is a more extreme value. A 99-degree Fahrenheit body temperature is slightly more extreme than a birth weight of 4,000 grams. Using z-scores to identify significant values, significantly high and significantly low is below -2 or equal to 2 or above. The lowest platelet count in a data set is 75. Platelet counts are measured in 1,000 cells per microliter. Is that value significantly low? Assume that platelet counts have a mean of 239.4 and a standard deviation of 64.2. We're looking at the lowest. We have z is equal to x minus x bar over s, which here is going to be 75, minus 239.4 divided by 64.2. This is going to equal negative 2.56. Since it's less than -2, here's -3, negative 2.56 is right about here. This is to the left of -2. It is significantly low. And that's really all we're doing in this section.